Can you make inference from a population with only a small sample size? Yes, and the tool for that is the t-test. Let's assume that the population that we're sampling is something normal. It has an average, which is what we're trying to make inference about, and it has a standard deviation, which controls how far observations are going to be from that average. We don't know anything about the population. What we do know is the values of a sample. And from that sample, we can get three numbers. We can get the number of observations that we have, which is usually small in this case. We can get the x bar, the sample average, and we can get S, the sample standard deviation. Now, the t-test is what? The t-distribution was defined in the 19th century as a ratio distribution of a normal distribution divided by a chi-square distribution. In this case, the chi-square distribution, once again, is going to be the variance of a population. It's a distribution of variances of samples drawn from a single normal distribution. So how does it relate to our sample? We're going to calculate these things from it. The denominator, or the numerator, is going to be a normal distribution, and that's going to be our sample average minus our hypothesized mean. So in many cases, that's going to be 0. I'm just going to write u here because it could be some specific value. And then we're going to divide that by our estimated chi-square variable. In the case of our sample here, it's going to be s divided by the square root of n. So that gives you how variable your sample is, controlled or scaled by how many observations you have. The result of this ratio is a number called t. And we assume that this is drawn from something called the t-distribution. What's that? The t-distribution, centered on 0, looks an awful lot like a normal distribution, except it's a little bit thicker. And the amazing thing, the source of its whole dark power, is that the t-distribution has only a single parameter, v, the degrees of freedom. So in our case, we need to know, is this value t going to be likely or unlikely compared to this t-distribution? We need to set this parameter v before we can answer this question. We set parameter v to n minus 1, the degrees of freedom of our sample, after having calculated the mean, which is what costs us that 1 degree of freedom. So now we look and see, where is t in this distribution? Is it a probable value, close to the middle? Is it unlikely, far out, and what are the tails? Let's say that it's an unlikely value. Then we can ask the question, is this unlikely value, what is the probability, rather, of having observed or calculated a t that is as extreme as or more extreme than the one that we found? In other words, the area under the curve in this tail here. That gives us a probability, and if our probability is low, that means that this t was unlikely. And then if we wish, we can perform the ancient frequentist magic of concluding that an unlikely observation means an unlikely hypothesis, and therefore our population mean, in this case the average difference, is indeed unlikely to be 0. And that is how you use the t-test.